everyone, I'm Josefina Cruzat, and I hope you are having a great time at the educational course and that you are learning a lot. I truly wish I could be there with you today, but unfortunately, due to circumstances that were beyond my control, it was impossible for me to travel. But still, I'm very grateful for the chance to virtually present our findings on psychedelics and brain dynamics. Okay, so serotonergic psychedelics like LSD and psilocybin are drugs that cause deep but temporary changes in how we perceive things and how we experience the world, right? And this gives us a unique look into the human mind and brain. And now with tools like functional MRI, we can link these mental experiences that arises to what is happening within the brain. And by observing how psychedelics change brain activity and matching those changes with shifts in our conscious experience, we can learn how different parts of the brain control consciousness and how by altering specific brain system, we can also affect our state of mind. And in recent years, this area of study has become more and more popular in neuroscience, but also beyond, because psychedelics shows also a great promise for treating mental health disorders, but still, we still don't fully understand exactly what is going on, how psychedelics work. And that is what motivated the research that I'm about to present today. So, taking a little bit of background, there is this idea that psychedelics drugs change how our brain organizes its activity, and that this change depends on how much of the drug you take, right? And we've got two big theories that have helped us understand this, which are Robin Carhart-Harris' rebus model and also the entropic brain hypothesis. And basically, both of these theories tell us that our brain operates like a smart machine, that it's permanently trying to predict what's coming next, and also at the same time is always adjusting itself based on the new information it gets. So it's by this, it's always working to minimize the difference between the expected and the received signals. The rebus model here, which stands for relaxed beliefs under psychedelics, suggests that psychedelics work by relaxing the brain's hierarchical processing, right? Meaning talking in terms of the primary to the secondary areas. Or in other words, psychedelics loses how the brain handles information, incoming information, meaning that there is like a fundamental reorganization of how sensory inputs are integrated and interpreted. So it's like a whole new way of making sense of how the brain makes sense of what it sees, feel, hear, right? Or like integrating all this coming sensory information. Okay. So, at the heart of this model is how these drugs interact with the serotonin 2A receptors, which are the main target of psychedelics, at least LSD and psilocybin, which are the ones that I'm going to mostly talk about. And these receptors are mostly found in high order cortical areas that are the parts of the brain that you know that deal with complex thoughts and higher cognitive functions. And when psychedelics bind to these receptors, there is like a significant reduction in the precision of high-level priors, allowing us for a more anarchic, bottom-up flow of information and making the brain's information flow more fluid, wild, less controlled. And at the same time, this changes the way we perceive and think about things, from what we see to how we understand ourselves. These reduced barriers allows the brain to explore its dynamical landscape more freely, and therefore it leads to an increase in entropy, making the brain activity, more random, more chaotic maybe, or more unpredictable. And this is believed to open up new ways for the brain to explore its capabilities. And the effect that we feel during the psychedelic experience, like, for example, seeing or perceiving vivid colors, feeling connectedness to the universe, or having experienced this ego dissolution, all these perceptions and feelings are of course tied to these changes. So understanding these dynamic characteristics help us figure out how psychedelic work, but also might help us treating various mental health conditions. The other theory is the entropic brain theory that I touched it a little bit. And this theory tried to explain consciousness directly by looking at the brain entropy. And the theory suggests that the level of one consciousness and the richness of the experience can be measured by the amount of disordered, unpredictable brain activity. So this hypothesis aims to understand psychedelic states by looking at the underlying neural changes. So when we say that conscious states are a function of brain entropy, what we mean is that the level of entropy in brain activity can indicate the level of one's conscious experience. And this is reflected in this figure from Carhart-Harris' paper, when you have lower entropy in brain dynamics, you are in more rigid states like coma, anesthesia, sedation. But when the level of entropy increases, you tend to have more flexible states that are related to the psychedelic state, infant consciousness, and all the states that are described here. So, having in mind these two theories, in this talk, I'm going to walk you through two different ways in which we looked at how psychedelics change brain activity and present findings that support the idea that these drugs relax the usual way of the brain to process information. Like in the Rebus model, changing this hierarchical processing, and also tying these results with the entropic brain theory. So first up, I will explain the turbulence framework we use to understand how LSD and psilocybin changes this brain functional hierarchy, allowing for a more global, freely flow of information, and allowing us to understand how these drugs allow this, like how they change the usual order of brain activity. Research of this turba means crowd. Start by the turbulent signatures in brain dynamics. As you may know, the concept of turbulence was first introduced by Leonardo da Vinci in the particular context of fluid dynamics. And the word turbulence, that came from the Latin word turba, means crowd. And why this is important is because Leonardo da Vinci was trying to explain or refer or to describe the irregular and chaotic movement of fluids by using the word crowd, like these swirling eddies that you see in water and in air, and in some of these beautiful examples you are seeing from nature. So back in those days, Leonardo da Vinci was fascinated really by how these chaotic movements had hidden orders. And he quickly realized that turbulence wasn't just a chaos, random chaos, but there was a structure or an order in it. And these discoveries led then to long-standing research in fluid dynamics that showed that turbulence facilitates the rapid transfer of energy through fluids. And this understanding of turbulence since then has become crucial not only in physics but in many fields. And now we are taking these ideas and applying them to the study of brain dynamics. Okay, so after Leonardo da Vinci, Kolmogorov expanded on this idea of turbulence with his phenomenological theory of turbulence, for which he used the concept of structure function, that was like a novel concept, which it wasn't related to what we understand in the neuroscience field of structure function connectivity. You know what I mean. So basically, what he did was to look at how the movement of any 2 points on a fluid separated by a certain distance were related, right? And this helped him understand and measure how energy moves and balance between kinetic energy and the resistance of the fluid. Later on, Kuramoto used the theory of couple oscillators to describe turbulence in fluid dynamics and also beyond fluid dynamics. And you might know that couple oscillators have been being used very successfully for describing large-scale brain dynamics, and in particular to describe the metastability of brain dynamics. So these findings suggest that turbulence could play a very crucial role in brain dynamics, just like it does in fluids, but instead of transferring energy, in the case of the brain, it might help with transfer information more efficiently.
Please, technical assistance, could you see why it stopped or move forward?
This was exactly what Gustavo Deco and Morten Kringelbach did. They used these ideas to study how turbulence in the brain affects its activity and information transfer. And in this framework, the turbulent core was or is determined by the local synchronization between different brain areas that in turn are linked to the rotational vortices found in fluid dynamics. And with that, they demonstrated turbulence in large-scale neuroimaging data from healthy participants scanned with functional magnetic resonance imaging. So, to figure out how psychedelics specifically change brain activity, we use this framework and two methods inspired in turbulence that were like the model-free approach and a model-based approach. So using the model-free approach, we measure information transmission across space and time using these four different measures that are turbulence, information transfer, information cascade flow, and information cascade. These measurements are all based on the Kuramoto order parameter, which describes how synchronized a brain region is as a function of space and time and at a given scale, which is the parameter lambda that reflects or determines the distance over which synchronization is assessed. Okay? Just the model, and we adjust the model to closely match the empirical functional connectivity patterns, and then to see how each brain state reacts to external stimuli, we apply in silico perturbations by moving the bifurcation parameter of the model. And we measure the functional consequences using two different and complementary metrics that are the susceptibility. This measure reflects how sensitive the brain model is to the perturbations, and it was calculated as the difference between the perturbed and unperturbed states, and the information capability, the information encoding capability, that measures how well the brain encodes these perturbations into the dynamics, and this was assessed by the variability in susceptibility across different trials. And what we found is that compared to a placebo, both LSD and psilocybin significantly increase turbulence in brain activity. We found that in LSD, increases in turbulence were found across all spatial scales, but the effect was stronger at longer distances in the brain. And for psilocybin, the increases in turbulence were only observed at longer distances. We also calculated the slope of the mean turbulence at different scales to represent the level of turbulence for each condition. Here in the figure on the right, and here we show how information transmission changes through time and space due to these changes in turbulence. And please note here that both psychedelics decrease the slope of turbulence at longer spatial scales. We then measured how information travels across the brain at different spatial scales using the information transfer measure, and we found that both psychedelics increase information transfer across spatial scales, making information transmission more efficient in the brain, and probably leading to what it has been observed before of the brain's overall increases in connectivity. And here we also measured how information cascades through the brain at different scales, and we saw that both LSD and psilocybin show very similar patterns at shorter spatial scales, which are the larger lambdas, but they differ at shorter scales, suggesting that psilocybin is more sensitive to changes in information transmission across scales. Then regarding information cascade, which describes the transmission of information across spatial and temporal scales, we found that both psychedelics show significant results compared to placebo, and this means that LSD and psilocybin both enhance the brain ability to transfer information efficiently across different regions and also times, with LSD having broader effects than psilocybin. We then measure how much the synchronization of brain regions varied over time using the standard deviation of the Kuramoto order parameter for each of the conditions, and we compare the similarity of node level turbulence between each psychedelic and their placebo counterpart using the Kolmogorov-Smirnov distance, which is a measure of similarity, and we found that the difference between conditions were more pronounced at lower spatial scales for both drugs. Interestingly, when we looked at the network behavior, we managed to identify the nodes with the largest differences, which were the ones contained in the upper 15% quartile, and with that we determine which resting state networks they belong to, allowing us to describe the specific turbulence-based changes in brain networks. And as you can see here, we saw that for LSD, the main differences were found in somatomotor and dorsal attention networks. And for psilocybin, the main differences were found in the default mode network, frontoparietal and ventral dorsal. Then for the modeling approach, we found that both drugs significantly reduce the brain susceptibility to external disturbances and significantly increases the brain ability to encode information, meaning that psychedelics make the brain less reactive to external inputs, while at the same time enhance its ability to process and encode information. And the overall findings are consistent with previous results, showing that psychedelic drugs appear to broaden the brain's dynamical landscapes and enhance global functional connectivity by shifting the brain's global working point towards a more globally connected profile. And also our findings advance the field by suggesting that psychedelics also promote a greater spread of neural activity and an associated increase in information transfer by mixing domains and scales throughout the brain. Okay, and with that, we now turn to our second study. And here we suggest that the increase in brain entropy during the psychedelics experience might be due to a flattening of the brain's control energy landscape. And for this, we use network control theory, which allows us to quantify how a system moves through its different states, and it allows us to measure the energy that is required or needed to transition between the states, which is known as control or transition energy. All of this is because we have in mind that even at rest, the brain is never static. It is constantly switching between different recurrent states, right? So, as I mentioned, we used network control theory to explore the relationship between the energy demands and the entropy during the psychedelic state. And for this, we combine functional MRI data, the one that I explained before, with structural connectivity from diffusion MRI, and also here we combine with receptor density maps of the serotonin acquired using PET from living subjects. And in this study, we hypothesized that the energy that is required to transition between different states decreases under psychedelics. And this is the cartoon is here. You see this versus this other one. And we believe that the reduction in the control energy will also correlate with increases in entropy at the individual level. So our first step was to identify the main patterns of brain activity. And for this, we used data-driven clustering and found 4 stable clusters of brain activity here, which we grouped in 2 larger metastates. So for the metastate 1, this was made of 2 metastates, 1A and 1B, this was made of the states that show opposing activation patterns between the somatomotor, here the somatomotor, and the ventral attention salience networks versus the default mode network. And in the metastate 2, also made up 2 substates, substate 1 to A and to B, showing opposing activation patterns between the default mode network, the somatomotor, and visual networks in opposition to the frontoparietal. And to identify the effects of LSD and psilocybin on brain dynamics, each of the subject's MRI scans data were characterized in terms of each of these 4 identified states we measured. And we measure here the fractional occupancy, which is how often each state occurs. We measure the dwell times, reflecting how long each state lasts. We also measure the appearance rate, which is how often each state appears per minute. And finally, we measure the transition probabilities that I'm not showing here, but I will show later, which is how often each state, the transition is the likelihood of switching from one state to another. And we found that for both psychedelics and placebo, the brain most frequently occupies metastate 1, which is here, with its substates being visited for the longer periods. So in terms of LSD, we saw that LSD increases the time spent in metastate 1 and decreases the time in metastate 2. There were longer dwell times in metastate 1 and shorter in metastate 2, and there were no significant changes in the appearance rates. And for psilocybin, we found no differences in fractional occupancy, no differences in dwell time, but significant increases in the appearance rate of two states, suggesting that LSD and psilocybin affect brain dynamics differently, possibly due to differences in drug onset versus peak effects, or also maybe to sensitivity to the different type of serotonin receptors. And we then tested our hypothesis that psychedelics decrease the energy needed to transition between brain state using the network control theory. And as this theory helps quantify how easily a system can move between different states. And in fact, we found that both LSD and psilocybin lowered the transition energy between all possible pairs of brain states, which is the minimum energy needed to move from one state to another. As controls points, we used different controls, like we used uniform inputs across all brain regions to calculate the transition energy. And we also consider specific brain regions where energy is injected, focusing on regions with serotonin, with more representation of serotonin 2A receptors, which are, of course, as I said, the receptors that are known to be mostly affected by psychedelics. And we investigated also the influence of these receptors, and we ran a validation strategy. And with all of this, we consistently found that LSD and psilocybin make it easier for the brain to transition between states by lowering the energy that is required. And also, we saw that this effect, it was especially linked to regions which are richer in the serotonin receptors. Okay. Then in our final analysis, we compared the effect of different serotonin receptor on the transition energy needed for brain state changes. And we saw that the 5-HT2A receptor was particularly well suited for reducing the energy required for brain state transitions, highlighting its role on the effect of psychedelics. But we also saw that the 5-HT1B receptor also shows significant energy reduction. So this highlights a potential role in the antidepressant effects of psychedelics and SSRI. And to conclude, so we found that LSD and psilocybin increase brain activity turbulence, enhancing information transfer and leading to richer and more diverse brain states. LSD affect visual sensory areas, while psilocybin impact high-level networks, expanding the brain connectivity and conscious awareness. Psychedelics reduce the brain's control energy, making it easier to transition between states, influenced by the serotonin 2A receptor, and also improve the brain's ability to encode and process information efficiently, creating a more interconnected and sophisticated state. Moreover, the serotonin 2A receptor significantly reduces the transition energy, playing a role in the effect of psychedelics. And overall, our approach aids in optimizing maybe drugs intervention, identifying biomarkers for neuropsychiatric disorders. And with that, I want to thank my amazing collaborators, because without them, none of this could have been possible. And of course, I want to thank you for your attention, and again, say sorry for not being there personally, but I hope you enjoy it. And with that, thank you very much.